Imagine this, flying from Tampa to China, Australia, or anywhere else in less than an hour. Flight engineers at the University of Central Florida are working on the secret to safe hypersonic travel. For decades, humanity has dreamed of reaching the stars, but the vast distances between Earth and even the nearest stellar neighbors have posed what seemed like insurmountable challenges to scientists, engineers, and visionaries. Interstellar travel, long confined to the realm of science fiction, has been a tantalizing goal, one that seemed centuries away. Now NASA has stunned the world with a groundbreaking announcement. The development of a light-speed engine capable of interstellar travel might finally be within reach. This revelation has sparked excitement, skepticism, and endless debate within the scientific community and beyond. What exactly is this light-speed engine? How does it work? And what does this mean for the future of humanity? To understand NASA's breakthrough, we first need to explore the challenges that have held us back and how scientists are overcoming them. The primary obstacle to interstellar travel lies in the distances involved. Our closest stellar neighbor, Proxima Centauri, is 424 light-years away. To put that into perspective, traveling to Proxima Centauri using our fastest spacecraft today, the Parker Solar Probe, which reaches speeds of about 430,000 mph, would take over 6,700 years. Clearly, achieving interstellar travel requires a revolutionary leap in propulsion technology. Traditional rocket engines rely on chemical propulsion, burning fuel to produce thrust. While this method has been incredibly successful for launching satellites, exploring the moon, and reaching other planets in our solar system, it is fundamentally limited. Chemical rockets are constrained by the energy density of their fuel and the sheer mass of propellant required to sustain high speeds over long distances. To reach even a fraction of the speed of light, a rocket would need an astronomical amount of fuel, making chemical propulsion impractical for interstellar missions. Enter NASA's light-speed engine. Unlike conventional rockets, this engine leverages cutting-edge principles from theoretical physics and engineering to achieve speeds that were once thought impossible. Central to this breakthrough is the concept of propulsion without propellant, a radical departure from the methods used by all previous spacecraft. At the heart of this new engine is an advanced application of Einstein's theory of relativity. One of the most revolutionary aspects of relativity is the understanding that space and time are not static but can be bent, stretched, and warped. This insight forms the foundation of what NASA's researchers are calling the warp drive. The idea of a warp drive was popularized by science fiction, particularly Star Trek, but it has real scientific roots. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical method of faster-than-light travel. Instead of propelling a spacecraft through space, the Alcubierre drive would compress space in front of the spacecraft and expand it behind, creating a warp bubble that moves the spacecraft along with it. Within this bubble, the spacecraft itself remains stationary, avoiding the relativistic effects of traveling at the speed of light, such as time dilation. For decades, the Alcubierre drive was considered purely theoretical, as it required an exotic form of matter with negative energy density to create and sustain the warp bubble. This exotic matter, often referred to as negative mass, had never been observed in nature. However, recent advancements in quantum mechanics and material science have brought this concept closer to reality. NASA's breakthrough lies in their ability to generate a warp bubble using principles derived from quantum field theory. Scientists at NASA's EagleWorks laboratory, led by Dr. Harold White, have been experimenting with a phenomenon known as the Casimir effect. The Casimir effect occurs when two uncharged parallel plates are placed extremely close together in a vacuum, creating a negative energy density between them. By scaling up this effect and applying it in novel ways, researchers believe they can generate the negative energy required for a warp bubble. In addition to the Casimir effect, NASA is exploring the potential of quantum vacuum fluctuations. The quantum vacuum, often described as empty space, is not truly empty. It teems with virtual particles that pop in and out of existence. By manipulating these quantum fluctuations, scientists hope to create the conditions necessary for faster-than-light travel. The light-speed engine also incorporates advancements in plasma physics and electromagnetic propulsion. Plasma, the fourth state of matter, consists of charged particles that can be manipulated using electromagnetic fields. NASA has been developing plasma-based propulsion systems, such as the Variable Specific Impulse Magnetoplasma Rocket, VSIMR, which uses electromagnetic waves to heat and accelerate plasma. While VSIMR is not a warp drive, its principles have informed the design of the light-speed engine by demonstrating how to achieve high thrust without relying on traditional fuel. Another critical component of the light-speed engine is its energy source. To achieve the immense power required for faster-than-light travel, NASA is exploring the use of antimatter. When matter and antimatter collide, they annihilate each other, releasing pure energy according to Einstein's famous equation, E1 mc wakam tantum mc tantu. Even a small amount of antimatter can produce an enormous amount of energy, making it an ideal candidate for powering an interstellar spacecraft. However, antimatter is extremely rare and difficult to produce. Current methods of antimatter production, such as using particle accelerators, are expensive and inefficient. To address this challenge, NASA is collaborating with international partners and private companies to develop new techniques for antimatter generation and storage. One promising approach involves using magnetic fields to trap and contain antimatter particles, preventing them from coming into contact with matter. The implications of NASA's light-speed engine are staggering. For the first time in history, humanity could have the means to explore other star systems within a single lifetime. Imagine a mission to Proxima Centauri that takes just a few years instead of millennia. Such a breakthrough would open up a universe of possibilities, from studying exoplanets in detail to searching for extraterrestrial life. Beyond its scientific potential, the light-speed engine has profound implications for the future of humanity. Interstellar travel could provide a solution to some of the most pressing challenges facing our species, such as overpopulation and resource scarcity. By establishing colonies on habitable exoplanets, we could ensure the long-term survival of humanity and expand our horizons beyond the confines of Earth. Be easy, but it will be worth it. As Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." With a light-speed engine, humanity is taking its first steps toward fulfilling this destiny. The future is closer than we think. The stars are calling, and NASA's light-speed engine may be the key to answering that call. Are we ready to embrace the challenges and opportunities of interstellar travel? Only time will tell, but one thing is certain: the journey has already begun. The societal implications of light-speed travel are profound. The potential to travel at light speed or faster is an achievement so transformative that it challenges humanity to redefine its identity and purpose. Historically, every significant leap in transportation technology, whether the wheel, the steam engine, or the airplane, has reshaped human societies in unpredictable ways. The light-speed engine, however, is not just a leap, it's a quantum leap. It may have far-reaching consequences for how humanity organizes itself, how nations relate to one another, and even how we define human civilization. One of the first and most obvious societal shifts could arise from the way humanity thinks about borders and resources. With access to other star systems, humanity would no longer be bound by the finite resources of Earth. Planets, asteroids, and moons rich in rare minerals, water ice, or energy sources like helium-3 would become accessible. This abundance could eliminate resource scarcity, potentially solving long-standing global issues such as poverty, inequality, and resource-driven conflict. On the other hand, it could also create new forms of competition. Who has the right to claim resources on Proxima Centauri b or other potentially habitable planets? Would interstellar exploration be governed by international treaties, or would it spark a new space race with echoes of imperialism? The history of colonization, particularly in the Americas and Africa, offers stark warnings. Without careful planning and ethical oversight, humanity could repeat past mistakes on an interstellar scale, leading to conflicts over territory, exploitation of alien ecosystems, or even tensions with potential extraterrestrial civilizations. Throughout history, exploration has expanded not only physical horizons, but also cultural and philosophical ones. Light-speed travel would expose humanity to the vastness of the universe in a way that even the most advanced telescopes cannot. This could profoundly alter our worldview. Religions, philosophies, and cultural narratives would likely evolve in response to interstellar discoveries. For example, finding microbial life or intelligent life on another planet could challenge deeply held beliefs about humanity's uniqueness. On the other hand, it could reinforce the idea that we are all connected, not just as a single species on Earth, but as part of a cosmic tapestry. Art, literature, and media would likely reflect this shift. Imagine films and books inspired by journeys to distant stars or music that attempts to capture the vastness of interstellar space. The light-speed engine wouldn't just transform our physical reality, it would inspire an entirely new era of human creativity. The economic implications of interstellar travel are staggering. The development and deployment of light-speed engines would likely create industries that we can barely imagine today. Much like the Internet revolutionized commerce, communication, and culture, interstellar travel could revolutionize sectors such as mining, energy, and tourism. Interstellar tourism, for example, might initially seem like science fiction, but it could become a reality for the wealthy elite within a few decades of the first successful missions. Over time, as technology advances and costs decrease, it could become accessible to a broader audience. Meanwhile, the extraction of resources from other star systems could disrupt existing economic models. How would the discovery of vast quantities of gold, platinum, or rare earth elements on other planets affect their value on Earth? Would interstellar resource extraction lead to new economic inequalities, or would it level the playing field by providing abundance for all?